So, good afternoon, everyone. I hope that everyone's going to have a great week. We are going to initiate and begin the second webinar. Actually, today's schedule is a series of webinars that comes from the collaboration between two projects, REWIRE and ENTRUST. Let's say in a series of webinars that let's say elaborate with cybersecurity awareness and entitled with Trust or Bust, giving emphasis in specific aspects of the cybersecurity for IT ecosystems. We take pride in having this collaboration with the Trust project as well, and great collaboration with between the two coordination teams and dissemination teams for hosting these webinars. And begin, let's say, the series. The first webinar took place on Friday, giving emphasis in the AI misbehavior detection that is part of REWIRE project, and today we are going to continue first with an introductory section from Sofianna, member of the technical coordination team of REWIRE, describing the vision as it is, let's say, merged and concurred between the two projects, and we are going to proceed with the main session that has to do with reinforcing the IoT interoperable security stack through crypto advancements and attestation mechanisms, and we take pride also for the panel composed by the two projects, REWIRE and ENTRUST, from universities and the industry, so that we can have a holistic overview of the IoT for complex ecosystems that it is elaborated within the context of the three projects. So I'll give the floor to Sofianna to have a brief introduction about the vision toward trustworthiness of systems, an issue that is elaborated between the two projects, and then we're going to continue with the main sessions, keeping up on the schedule. I think you can begin.
Okay, thanks, Thanassis. Thank everyone also from my side for joining today. So in this first presentation, I wanted to do an introduction on REWIRE and ENTRUST projects and set the scene on what will be the focus of this second webinar. So in the context of the entire compute continuum, which means that there is a service graph chain consisting of multiple devices, medical devices or different type of devices and infrastructure elements that can host services, there is a crucial need to enhance trust. So there is currently in the literature a lot of effort on how to enhance the security profile of a device, but all these works are mainly focused on the integrity part. However, when we getting closer to what is described in the standards, we can see that trust and trustworthiness is not only integrity, but also are different properties such as reliability, safety, and so forth. So there has been quite an extensive definition on all these standards, and most of them have converged that we need to cover a wide gamut of properties that we need to guarantee in order to assure that a device is in a correct state. And this is what we are trying to achieve in both REWIRE and ENTRUST projects. Now, when it comes to the concept of trust, we have two flavors. The first one is the type of data source, which is actually the devices, and this is what we call a node-centered trust. And the other one is the data center trust, which is the trust level we try to check the communication of the messages to be exchanged between them. So we try to combine both data center trust and node center trust in order to characterize the trust level of specific devices and then the whole service graph chain. Moving next, the common denominator in order to do that is we have to assess the evidence we take from the devices, and this needs to happen in a verifiable manner. So we don't trust when we don't trust the evidence and have some uncertainty on our opinion or characterization of the trust level of the device itself. This is the reason we need a rich set of mechanisms and protocols that are able to provide the secure lifecycle management of the devices, starting from the design phase that allows the device to be equipped with all the appropriate tools, and moving to execute its trust assessment protocols and establish the actual trust level or re-establish the trust level if something is not going okay. What we are doing in REWIRE ENTRUST is basically we provide all the protection mechanisms supported by a wide range of different underlying hardware-assisted root of trust. And the core message here is that we need this type of security mechanisms to convert the actual device to a hardware-based security token and provide this verifiable evidence. Now, there are some important challenges at first we need to cover. And the first one, which is directly related to the verifiable evidence, is to characterize the trust level of the device when we have contradicted data from multiple adjacent devices. So currently we can use, in the literature, let's say there are several probabilistic logics. And for instance, in REWIRE, we assume that we consider these tools ready and we don't focus more, but in trust, we provide an existing trust assessment mechanism based on subjective logic. Another important thing is what type of evidence we need to monitor. Of course, the evidence should not be overkill on the device, and in tandem to be rich enough to allow the accurate trust assessment regarding the device. So one important thing to establish this is the remote attestation mechanism, but what we do in REWIRE is we minimize, but in the literature we can say that most works try to cover the whole space, but this is overkill. So in REWIRE we somehow minimize this space and have more better results. And we don't attest the entire software stack, let's say. So a key requirement on both projects is to converge trust and safety. And we can see that this is very crucial, especially of the medical related projects and devices, and don't have a very resource heavy security controls to achieve this. Here we highlight very briefly the objectives or the trust enablers of REWIRE on the left and a trust on the right. As we can see, there are several common objectives and trust enablers in both projects. In general, REWIRE focuses on runtime attestation and verifiable monitoring, focuses on the open hardware architecture such as the RISC-V, while ENTRUST focuses on medical devices where we have a different type of root of trust, the OP. And in this project, we also expand the runtime attestation to SWARM attestation. And on top of that, ENTRUST offers also the trust assessment framework, which is with more advanced crypto and also more advanced crypto for the onboarding processes in this project. As we can see, both projects are complementary and can offer a very rich tool of trusted computing extensions and security enablers for the dynamic trust characterizations of devices. And closing, here is the list of operational phases of both projects. In the left is the REWIRE, on the right is the ENTRUST. I will focus on the ENTRUST, which is more phases and cover the ones from REWIRE. So regarding the design time phase, we bootstrap the trust of the medical devices based on the mood profile. In the pre-deployment phase, we perform the device onboarding, where we have new mechanisms regarding the ABS crypto scheme that we will see later in the presentations. Also, in the actual runtime phase, we have the trust assessment mechanisms, and we provide how to establish and how we establish trust. And we have also schemes such as the software update that will be over an authenticated and encrypted channel. And finally, the last phase is the trust auditing phase. We can audit the trust assessment output based on conformity certificates. So that's all from my side. I can give the floor to the next speaker to present the software firmware update process with authenticated encryption and storing leakage protection scheme. If you have any question, of course, let me know.
Thank you very much, Sofianna. So I would like to introduce and give the floor to François Connet and Corentin Verhame from UCL to discuss about the LRBC SIM for securing software and firmware updates using authenticated encryption. So I think that François and Corentin, you can take the floor.
Yes, thank you very much for the introduction, and hi everyone. Can you hear me properly?
Yes, it's great. A little bit louder if you can. It's great.
Okay, like that, will it be better?
Yes, great.
Okay, can you see my slides too?
Yes.
Okay, so hi everyone, I am Corentin Verhame from UCL, and in this webinar we will talk about software updates and what we did in the context of the REWIRE project. So UCL's involvement in REWIRE is made of a few parts. First of all, the goal is to ensure secure transmission of software or firmware updates, because those are a very crucial point. Failure in that aspect would be dramatic, because anyone could execute any code, any desire of code, and rogue code, for example. The little specificity of it is that we are considering not only classic adversaries that are able to do cryptographic attacks, as we can like informally coin it, but also physical level attacks. What we mean by that is to consider a very strong adversary that is able to make measurements on some physical aspect of the chip, such as the timing, the power consumption, and all those kind of stuffs that are usually coined by side-channel attacks. In the context of the project, what we did is to propose two secure software update algorithms that encompass both the security of the classical attacks and the one from the side-channel world. The first one, is the one-to-one mode that uses LRBC2, which is an authenticated encryption mode of operation. It is symmetric cryptography, and it essentially allows to connect the device to the software update providers and to perform the software update in a secure mode. The second one is the one-to-many, where you can connect the software provider with many devices, and it uses digital signatures, which is some asymmetric cryptography, And we also have some symmetric for acknowledging that the communication process has been properly done. The schedule of this presentation here, first of all, we will give a bit of background on cryptography. We will speak about symmetric cryptography and leakage resilient cryptography, which is a bit more specific. After that, we will talk about evaluation that we did on a construction that is called the LRPRF, but we will explain what it is before. And then we will give a few slides on the evaluation of a commercially available protected core, protected AES core. So the first concept from symmetric cryptography we want to present is the AES. I think you know about it, but the core idea of the AES is that it's a block cipher. It is a standard that is widely used, and many technological development about it are already done, such as coprocessors and stuff. Essentially, you take an n-bit message and you obtain an n-bit ciphertext. It's encrypted under a given key, and you are very happy about that because it satisfies some security definitions that are kind of precise. What we depict here is the ECB mode of operation, so it's already going one step further because we can consider arbitrary size plaintext that becomes some arbitrary size ciphertext under a given key. This allows us to introduce the authenticated encryption, which is a mode of operation. So going one step further than just AES, you can use it in a mode of operation. Essentially, this, as we displayed here, a set of algorithms that provide encryption and decryption while achieving some security notions. The core idea here is to say that we can take arbitrary size message, we encrypt and decrypt them, and we have a few security notions. The first one is authenticity through unforgeable encryption, which essentially states that if you do not have the knowledge of the secret key, you are unable to create some ciphertext that will lead to valid decryption. So if you know that your adversary cannot forge encryption, you know that ciphertext that you receive are authentic. The second one is an indistinguishability under CCA, which is more simply coined by confidentiality. It is the goal of that property is to ensure that observing two different ciphertexts, one cannot distinguish them, and one cannot in the end recover what the plaintext was about. So those notions are used in the context of what we coined before classical cryptography, so without considering the side channel. And the core idea here is that it is covered by a precise definition, the proof that anything unwanted, so recovering info on the message or further message, boils down to a problem with the block cipher. So you can use the property of the block cipher, set it at a higher level, which is the mode of operation, and then you cannot do any of those rogue kind of operation. So if the block cipher is good, the encryption is secure. This is the goal to ensure security against classical attacks. Now, when we consider leakage, we have many additional possibilities. The cryptographic implementation can lead to an increased attack surface. So, for example, one can use the timing of the algorithm that may be dependent on some secret to recover information. To tackle that issue, the most common, the gold standard is to do constant time implementations, which is not so hard to achieve for symmetric cryptography. It can be more challenging in other contexts. You can also use physical emanation. We set that as a very high-level idea because physical emanation can be many things. It can be the power consumption of your chip during runtime. It can be the EM, so the electromagnetic waves that the chip emits. It can be many things. So whatever is physically dependent on the intermediates. You can also have more active adversary that can do fault injection. So they are able to change the execution that is made on the chip, and you can have therefore some information about the computation that is. To withstand that kind of adversary, which seems already kind of powerful, a field of cryptography is mainly used, and it is called leakage-resilient cryptography. The general idea to protect against sentinel attacks is to hide the signal into noise. It can go through mostly three ways. The first one will be more physical countermeasures that are very much at the electronic level, such as dual rail or clock jitter. The core idea here will be to limit the level of noise. So those are very electronic principles. With clock jitter, you will have more uncertainty on your signal, and with dual rail, you will reduce the consumption and the data dependence of the consumption. Implementation level countermeasure, for which we mostly describe like masking and shuffling, which aims at kind of for masking, improving the noise by hiding the signal into noise. Those are solutions that are quite well known and that are being well studied in literature. Another path is mode level countermeasures. This one is maybe a bit less studied in literature, and mostly we describe here in this context two aspects of it. The first one is the leakage resilient, so the random function, which we call LRPRF, and the last one is leveling, which is a nice mechanism to improve efficiency of mode of operation. Since those topics are maybe a bit less studied, the relevance still needs to be assessed. And that's here that we come into play with you, Sylvain. Because in the context of REWIRE and the software updates, the first idea will be to go with the primitive level countermeasures, so to design a protected core, use implementation level countermeasures, so masking, shuffling, maybe a combination of those, even if it's not working as gracefully as you would like. And partial proofs are possible, but they remain complex. Not only that the proofs are possible, but some implementation mistakes can have dramatic consequences. Since you rely on some very precise computations, even a small mistake would potentially compromise the security of the system. On the other hand, when you consider mode level protection, what you have is that somehow the security is embedded in the functionality. So the security relies on the algorithm, and you can mathematically prove the security with respect to the algorithm. So you have much less implementation hassle, because if you have something that is functionally correct, you know that you also have the security. And one nice feat is that it relies on off-the-shelf and protected core. This is the mode of operation, LRDC2, that we use in the context of REWIRE in the one-to-one use case. It is a mode of operation that allows you to encrypt many messages, which is depicted in the red part, and you output many ciphertext under a key. The key is taken, as you can see, in the first block, the TDF block, and in the last block, the TGF block. A nice feat that you can already observe is that along with those keys that you can denote as master keys, you will have other intermediate keys, so K1, K2, and K3, which are close to the XORs, the upper XORs. Maybe if we decompose a little bit that scheme, what we have first is the gray box on the left, which is the key derivation function that allows you to generate a temporary key. So that KDF is in gray because it uses the LRPRF to make a secure generation of ephemeral key. Essentially, what we do is that in that box, you use a nonce, so a public value, in a key that remains secret, and you're able to generate K1 that is dependent on the nonce and the key without revealing anything about the master key. So K1 is safely created. It is then screened to make the generation of your ciphertext. And at the end, it goes to the TGF, which is also graded, so also protected, also using the key to generate a tag. So the TGF, the tag generation function, it generates a tag without any leakage. All other intermediates are on white, and so they can be recovered, yet they will never compromise the secret, because K1 depends on K, but K1 cannot be tied back. Leveling here is the use of light non-protected cores that is secure thanks to the heavy KDF or TGF. So inside of those gray area, we require to have the side channel protection. So we have the LRPRF here, which is depicted on the right. It is that tree-based construction where you have many possibility of AES execution that is indexed by the plaintext. So if you just look at stage 1, you will have 4 possible AES that are indexed by P0, P1, P2, or P3, which share some possible plaintext, and it uses as input the key. So the core idea here is to observe that the long-term key K is only used in the first AES block. In terms of side channel security, it is very important because it means that it will only be used one and only under P0 or P1 or P2 or P3. So you can observe only 4 different leakages of the master key. So this already gives us a nice security parameter, which is the number of possible plaintext under which you encrypt. If you use a very small number, you will have high security, but you will have less performance because it will take longer time. The other way around, if you use a very large number of encryption, you will be very fast, but you will have a lot of observable leakages because you can observe 2 to the n a different encryption. So the core idea here is that PRF allows to bound the number of observable encryption. You can only observe 2 to the n encryption, and so it allows you to reduce the signal you're emitting on that key. You have that trade-off as recurrent between efficiency and security, and to assess that, the only way we can go is to go experimentally. We have to use one implementation of the AES, and we have to experimentally evaluate it to check if it is working nicely or not. So our evaluation here, it is made using that setup. So we have the target that is connected to the scope. We will make some source codes on the target for which we have the control, and we will recover the intermediate value, so xi, and the leakages from the scope. We can do some model estimation, and we will use that model estimation to perform the best attack possible. So we set up the targets, we make the measurement, we make the connection with the measurement device, we make it as best as possible, so we have a bit of electronic engineering in there. The source code is run on the target for selected intermediates, and the models are estimated on collected leakages. In practice, it looks a little bit more messy than this nice diagram. It looks kind of like that, where in red you have the targets that you will connect in yellow to the probe. The probe goes to the measurement device in blue, and everything is connected to a server which allows you to flash the target with the source code that you require, to collect the data, to store them, and then to make the model estimation. We also have a kind of post-processing idea where we will build the model and evaluate the quality of the model to ensure that we take the best possible models and we are able to conduct some good attack. So, when we are back to that LRPRF, we can finally conclude on the security, on the trade-off between security and efficiency by giving that kind of plot. So we did the practical evaluation, we built the model, and then we performed the attack on the PRF. What you have here is your answer to the trade-off between efficiency and security, because your x-axis is efficiency, it is the parameter n, so the log of the number of plaintext you're able to encrypt in the PRF, and the y-axis is the security, it is the guessing entropy, so the number of bits of the key that you will need to iterate over to recover the key. What you can see is that you have 3 curves because it concerns 3 different levels of averaging. So the blue one is when you have no averages, so you just take the traces as they come. What you can see is up to like 5 or 6 you still have a security above 100 bits. This is something that you may consider sufficient, but what we show here also is that if you consider averaging, so if you average your observation 32 times to reduce noise, the parameter number 6 already becomes below 100. And if you average even a significant amount of time, you will have to select a parameter of 4 or 5. So this is our answer to the PRF, and its relevance is that yes, it can be used. We can see that for a very small level of encryption for a very small security parameter, you still have a security level that is very close to a plain AES key, so 128 bits. Now, what we also did is to make the evaluation of a protected core. In fact, what's interesting here is that we used the same methodology as for the PRF, and the core idea here was to assess the validity of our approach, to see if everything was coherent and nicely done, and to be able to perform a comparison with a protected commercial core. So the setup is exactly the same, just the target is changing. It's not more a plain AES ECD, it's an AES ECD still, but a protected one. So you have some implementation level countermeasure. The methodology is exactly the same, but it becomes more challenging. Why? Because you have unknown countermeasures and some secure engineering to reduce the access you have to the device. In term also of equipment, it stays exactly the same. Same methodology, same equipment. So we can claim that we have the same power for the other side. Now, when we do the evaluation, what we observe is that what you have on the right plot on the top is that you have traces. So power traces. You can see that they are kind of messy. And the very nice fact is that on the bottom, you have the signal-to-noise ratio, and you can see a few peaks. So what you can see is that you have some signal-to-noise ratio. So despite the fact that you have some unknown countermeasures, you have some SNR, hence you have some signal. SNR, signal-to-noise ratio, it is a statistical measurement that gives you the amount of data-related information you can get. In fact, the term information is kind of improperly used, because with the SNR, what you're observing is a difference of mean. So what you know here is that you will have a difference of mean in your traces for the time indexes that are spiking up, and you can exploit the difference of mean to obtain information. Intuitively, still, a higher SNR shows side channel attacks that will be more efficient than another. So you would like to in terms of electronic engineering, you would like to improve your setup such that your SNR becomes higher and higher to have the best possible attack. So the main message here is that the protected core can be attacked. This is something that we show here on the bottom. Since we were able to have SNR, we were able to have that difference of mean, we built the models, we selected the best possible model, and finally, we conducted the attack. And you can see that you have exactly the same kind of plot as before with the PRF. In X is the number of traces you're able to observe, and in Y it is the entropy of the key. So we can see that those are for average traces. So we made a bit of post-processing to improve the signal quality just by averaging to remove noise. Well, to remove the noise that is possible to remove. And so what you have here is you have your security level according to the number of traces, and you can see that if you observe up to like 5,000 traces, you're already at 100 bit of entropy. Something else, which is a little bit more of a side note, is that with reverse engineering, we can learn about the core. This is a nice observation that we did, is that on that protected core for which we knew nothing about, doing SNR on the full round, so this is the right plot, only the SNR, you can see that you have some data dependence that evolve, and you have twice the data dependent execution, which is most likely a countermeasure against fault attacks. We would like now to reflect a little bit on what we did for the PRF and what we did for the masking, the first question we wanted to answer was, can we achieve physical security without dedicated primitives? To what we answered that performing the security evaluation on the AES core allows us to conclude that it's suitable for embedding in a PRF that has some nice security guarantees. We can therefore use it as a conjecture in the RBC2 proof. So from the primitive, the PRF, we're able to put it in the RBC2 to satisfy the requirement that the PRF is leakage resilient. And we can achieve the required sustained resilience for the mode of operation and for the software complete. Now, another question was, what is preferable between dedicated and non-dedicated primitives? To which we will give a more nuanced answer. So for masking, we have a few advantages, which is the flexibility and the fact that you can, for example, use a communicate between a protected and unprotected implementation and obtain the same result. It is, however, hard to design and hard to evaluate, which are two features that are likely to impact the security level. On the side of the PRF, what we have is that it's simple and fairly easy to verify. However, the overhead is constant because you will always use it in a leakage resilient secure mode. Therefore, you will always pay the cost of it. As a final conclusion, what we want to say is that we achieve provable ciphertext integrity with leakage with LRBC2. We have our work that provides the comparison more in depth. What we presented here is part of that work, a comparison between the PRF and primitive level countermeasures. Both solutions are really interesting, and depending of your scenario, what means you want to set in a project, or what is the security that you want to achieve. Both are possible, and the PRF is competitive, even if it is a little bit less investigated in literature. And what we also did is additional work on primitive level countermeasure. So maybe we can present that as a nice application to Ascon. Ascon is the NIST lightweight cryptography competition winner, so it has been selected as a new standard, so it's quite timely. And what we did is look at Ascon and check whether it was possible to make some efficient masking for it, because Ascon is a very specific structure. And what we showed is that due to that specific structure, you can have some potential security trouble, and you need to be very careful when implementing it. So this work is very much in line with the first one, because in the first one, we say that masking needs to be well designed, and it is not straightforward. What we show for Ascon is that it is indeed not straightforward, and we propose a solution to tackle one issue that you can have with some physical defaults. Yes. So I would like to thank you for your attention, and if you have any questions, I will be pleased to answer.
Thank you very much, Corentin. Exactly right on time. I don't know if there is one quick question to pose to Corentin to keep the momentum before we proceed with the next presentation. Don't see any hand raising or posing a question, so we can proceed with the introduction of the next session. Thank you very much, Corentin. And I would like to introduce Samira Bronchos from NEC and Annika Wild from RUB, the University of Bochum, to give their presentations about the secure software update on trusted applications in RISC-V systems.
Hey.
Good afternoon, Samira.
Good afternoon. Let me know if you can see my screen or not.
In a while, probably. I can see dark screen.
Okay, that's something.
I'm expecting to see some code written. Not yet there.
If it doesn't work, maybe Anika can share the screen, because I don't know why it's not working.
Yeah, sure, I can try. Give me 1 second.
Okay, thank you.
Yeah, that's great. Thank you. So the floor is yours.
So on this presentation, we are going to go through the secure software update on trusted applications in RISC-V systems. And for this, I will first go through the definition of the ISAs, what an ISA is, what RISC-V is, what options it provides, how to build trusted execution environments, what is the REWIRE approach for doing so, and also, then Anika will take the floor and present the REWIRE update functionality and some demo on how it works. So, when we're talking about ISAs, we refer as an instruction set architecture, and we basically mean the set of instructions that a computer can understand. That's basically the set of assembly instructions that are available to implement whatever application we want to implement. In this case, the ISA will define how the software can control the CPU. And the ISA is usually defined by whoever is implementing it. Usually it's x86 or Intel, AMD, ARM, RISC, whatever processor manufacturer is implementing the CPU. This instruction set is usually given by the manufacturer in such a way that whoever is implementing the compiler or any application knows what to expect from the instructions that are going to be executed in the machine. But as a difference with previous approaches, RISC-V is purely based on open source principles. It was designed by Berkeley. Initially, they were using it to teach the students how to build CPUs, how to build computers, basically. And it was triggering so much interest and so many requests to open source it that they decided to do so. They created also some foundation and made sure the ISA is going to be open and free for everyone that wants to implement its own CPU without having to pay any kind of license or royalties. The only thing is, when we are talking about writing the definition of the instructions and the specification, it has to be only members from the RISC-V Foundation, the ones who can actually write the specification and ratify them, but anyone can become a member, so it's still free and open and so. And basically has like a base ISA, and on top of that base ISA, they implement different things. So this, so RISC-V is also a modular architecture. And by modular, we mean that they define some base instructions that are part of each of the modules, and each manufacturer defines or decides which ones they include in their RISC-V processor. When they made such decision, they have to put kind of a name or indication in the CPU, so everybody knows what is included in that CPU. And there is usually some confusion between an instruction set architecture or the architecture and the microarchitecture and some other things. So when we talk about the ISA, we try to answer this question, like what instructions do we have available? What are the other chain modes? What is the format of the data? Is it 32 bits, 64 bits? Which registers do we have? How do we handle exceptions or interruptions? But the ISA does not specify how an instruction is going to be implemented. How fast should this instruction execute? How much power it should take? How should we call whatever procedure? What is the replacement policy in the cache, or what is the size of that cache? What happens if there is a page fault? These are generally decided either by the operating system or the manufacturer, and this is usually referred as the microarchitecture, which you probably have heard about when hearing about microarchitectural side channel attacks. So why do we go for RISC-V? As I said before, RISC-V is open source, and there are already many softcore implementations. Softcore are basically implementations for FPGA boards that anyone can synthesize and load into the FPGA. And now there are even some hardware implementations that are also possible to use. This is an open source implementation, and anyone can touch into the hardware. Many details of the hardware might be available. And note that if you pick one softcore, then you have the details, but if you pick a closed implementation or already fixed implementation, the details might not be available. If you have all the details available about the hardware, then you can say, or you can claim that you can avoid the security by obscurity, basically, but by not knowing what the hell is going on inside the CPU, you cannot protect your code. Also, RISC-V allows some customization. So basically, if you decide you need another instruction that is not included in the ISA to implement any cool application you might be thinking about, you can basically add it, and that's totally fine. Also, because of these facts that it's open, it's free, and anyone can play with it, it's creating a growing community, and this applies for both hardware and software. Because if there is cool hardware, but there is no software that can run on that hardware, it's usually worthless. So it's nice that both communities grow at the same time. Another reason to pick RISC-V for projects such as REWIRE is that it allows many different contributions and to detect different security threats, to kind of patch them and fix them before the release goes out and it's available to everyone. And again, and to repeat one more time, it's open and it's free to use. That doesn't mean that if someone else implements a CPU, you are free to take it and use it. That will depend on whether the community, the person, the company, or whoever decides to open source this implementation or this software for RISC-V. So when we in REWIRE, we are trying to protect different implementations or different pieces of code from different partners and different stakeholders. And in doing so, we are planning to leverage trusted execution environments. We know how to protect data at rest. Basically, we encrypt the data into a hard drive and let it stay. We know how to protect data when we are transmitting data, but the idea of this is just to protect the data when this data is being used during runtime. So generally, trusted execution environments are defined as some isolated and secure areas of the main processor where the code and the data are protected. That basically means that unauthorized entities from outside this TE or enclave cannot read data inside that enclave. Also, these unauthorized parties cannot modify the code. And this includes the operating system and the hypervisor. That means if you want to outsource some applications to the cloud or to any environment, you can basically trust that the hypervisor or the operating system cannot read your data, cannot manipulate your data, and so on. When we talk about TEs, we assume that both the hardware and some specific privilege code are part of the root of trust. The root of trust is basically kind of all the set of elements that perform the critical operations can always be trusted, and if they crash for whatever reason, all the security guarantees of the system are lost. Usually the TEs provide some kind of mechanism to the partner, to the clients that are using the TE to verify that their code is actually running inside the TE. Because before the TE is completely set up, this code is can be read by anyone. Let's say. So the usual approach is you usually verify through attestation that your code is going to be run or to be executed inside the TE, and then you assign the secrets to that TE. There are different approaches or different solutions for building TEs. Some of them are proprietary, some of them are not. There is this global platform that open source, well, it's not open source, but they propose a standard API, and there are many. It's mainly meant for ARM, but many applications or many TE solutions can be built based on that standard API. The idea is that either if you're using Intel SGX, Truston, SEP, or any other TE solution, you can just call this standard API and perform the same operations regardless of the environment. As I said, there are different solutions. Some of the commercial ones include SGX or Truston, and AMD SEP, and so these approaches usually include some specific instructions in the instruction set architecture to be able to run the TEs. But in the case of RISC-V, we have Keystone. Keystone doesn't include any kind of hardware extension or so. Could you move to the next one? So the idea of Keystone is basically use the specification of the RISC-V course and build on the security monitor layer. If you look at the left side of the picture, you see that the standard defines different privilege modes. The one that has the highest privilege is the one that is called machine mode or M mode. Keystone is basically an open source implementation of that layer. That layer, you can see it as a privileged operating system that has completely access to the hardware and offers as an intermediation between the operating system and the hardware, or between the user mode applications and the hardware, or any other functionality that the security monitor wants to offer. Basically, this security monitor allows to leverage some features on the hardware to build the enclaves and to isolate applications. This is done through the physical memory registers or PMPs, and that basically enforces the isolation between all the enclaves. So if you move to the next one, please. One way to offer more functionality is to basically extend the keystone layer or to extend the security monitor layer. The keystone security monitor is basically known as an SBI, a supervisor binary interface. Is this interface between any kind of supervisor execution environment, that will be the operating system or the runtime that is placed inside the enclaves to just give them some functionality, and just offers some equals or some interfaces to the operating system or to the enclaves to just execute whatever code. The idea of the SBI is that it's also kind of, there is another standard for the SBI, so the operating system can build on top of it. Assuming that it has these functionalities, then the operating system can call the SBI to configure whatever layer. And this is basically what REWIRE is doing. If you go to the next slide, please. The idea of REWIRE is to avoid modifying all the hardware, and all the functionality that REWIRE offer is purely based on the features that are part of the RISC-V implementation. That means no modifications of the hardware are required to support the creation of the enclaves, and that also means that it's compatible with any RISC-V processor. So any processor that is compliant with the RISC-V standard, it's able to run the REWIRE security monitor. That doesn't mean if the CPU includes one, or if the hardware includes some crypto coprocessor, this could also be used by REWIRE. If you go to the next slide, please. So what we did in REWIRE, or what we are doing, is we detected some missing features in the keystone architecture, or in general in some enclave architecture, and we just enhanced the security monitor with such features. Such features include, for example, data sharing, key management system, enhanced attestation protocols, some approaches to trace the execution of binaries, enclave migration, and the subject of the next part of this presentation, that is some functionality to update the code inside the enclaves, which is usually fixed and bounded to a processor and has some limitations. But that's now what my colleague Anika will tell you.
Yes, right. Thank you. I'll now proceed with some details about the software update process. And I think the need for updating software in the context of the secure lifecycle management of device is out of question. So I guess everybody's aware that there might be security issues that require an update or functionality extensions or whatever. And commercial TEs, however, only allow the migration of state between enclaves if the developer key is the same. And for this, they have to pay with more lax security guarantees for the enclave data, which is why we opted in REWIRE to design a new update protocol for keystone enclaves. However, this is not straightforward, and there are a couple of challenges when designing a secure update protocol for enclave software. First of all, we need to prevent the rollback to previous and potentially insecure versions of the software. If this were allowed, an adversary could just start an older version of the software that, for example, has a known bug, and then they could just exploit this bug in this older version. Furthermore, we need to ensure that state synchronization between the terminated and the updated enclaves, because otherwise if the old enclave advances its state after transferring it, the state update will not be reflected by the new enclave version. And last but not least, we also want to provide strong evidence that the update has been installed correctly. All right, in the context of REWIRE, as I already said, we designed a protocol that overcomes those challenges and provides a means to update the enclave software securely. I'll now give you a high-level overview of the 4 main steps of this protocol as we implemented them in the context of REWIRE, and afterward I will give you a quick demo with a sample enclave where you can see how we realize these things. The first step of the protocol is the update trigger, and there are basically 2 types of triggers for an update. First, an update can be triggered when the REWIRE risk assessment process identifies a threat. Such a threat could be, for example, failed attestation of the software or a vulnerability that was detected through design time formal verification process. And of course, an update can also be triggered when there is new software version introducing a new feature or functionality to the software. In both cases, the developer generates an update package, and this update package consists of 4 components. The first component is the updated software itself. Then second, we have a software ID that is assigned to the software, and it is consistent over all versions of the software. So we can always identify this piece of software using the software ID. But the software version number identifies a specific version of the software, and thus should also be increasing with each software update. And finally, the developer also signs the software, the ID and the version with its private key, and publishes this update package to the blockchain. As introduced in the previous session, we have 2 types of updates, the one-to-one and the one-to-many update. A one-to-one update is intended for one specific device, and in this case, the developer can optionally encrypt the update package with the software update key of the target device using the REWIRE LRBC mode of operation. And this mode provides an authenticated encryption with resilience against key leakage attacks, as we already heard. And furthermore, the update can only be decrypted by the target device so that we gain update confidentiality. In the one-to-many updates, on the other hand, the update is intended for multiple devices so that we cannot encrypt it with a software update key because it is device specific and thus cannot be used for encryption. And this is why we do not encrypt the update here. Once the update has been published on the blockchain, we come to the third step, which is update verification on the target device. First, the update service on the target device fetches the update package from the blockchain. It then starts a host for the updated enclave, and this host then queries the security monitor to initialize an enclave with the updated software. After initialization, it's called a new run update SPI call that we implemented. And here the security monitor basically verifies the updates. That means it verifies the signature of the update to ensure the integrity of the update package and that the requester, so the developer, is actually authorized to publish and install the update. Then the software is checked, the software identity is checked to identify the enclave that is to be updated. And last but not least, the security monitor also checks that the version number of the update is higher than the one of the currently running enclave to defend against software rollback attacks. After successful verification, the update is then installed, and for this, first the security monitor attests the updated enclave using the REWIRE enhanced CIV attestation scheme that is also developed in the context of REWIRE, and you will hear more details about this in one of the next sessions. And this attestation then yields an attestation report, which the enclave forwards to the side-channel resistant AE enclave. And this enclave is the only component that has access to the software update key on the device. So it uses this update key to encrypt the report, and the security monitor then sends the encrypted attestation report back to the software update service, which verifies the report and sends an OK message back if the verification is successful. And in that case, the security monitor then finally runs the updated enclave, which triggers the old enclave that provides a snapshot of its state. And then the security monitor isolates the old enclave so it cannot receive any further calls from the host anymore. And this is it with the abstract theoretic part, the presentation of the protocol. I'll now quickly switch over to a demo video and explain to you what exactly we did in the implementation. Just give me a second.
Just try to keep a little bit space for the workflow, Anika, please.
Yes, sure. All right. So I'll now showcase the flow of the update process using a simplified demo application. This application just asks the user for a 4-letter input and stores it in the enclave state. And upon each input, the enclave outputs its entire state just for visualization purposes. So on the left terminal, you will see the original application. On the right one, we will do the updated application. And in between, there is some mediation going on. All right, so at first, we start the original application. And because Keystone binaries are compiled in a dedicated format, this format is first verified and decompressed before it actually gets executed. And then the host initializes the enclave and sets some parameters. Most important or most interesting for us in the context of the software update are the software ID and version that we already heard about before. And then there's also some setup of functions that allow the communication between the host and the enclave application. And most interesting for us here is the check update wrapper function, which basically is in a busy way regularly checking if the update is scheduled for, if the enclave is scheduled for update. And I'll give you a little bit more details about this in a bit. Also, at the very end, we can see that the actual enclave functionality waiting for an input. So we just provide an input and can see that this is made it to the actual enclave state. After all this, so we then start some helper functions. This is more important in the context of the attestation, and I suppose you'll get some more details later on. So at first we attest the enclave using the CIV attestation, which, as I already said, you'll hear about more in a bit. And then we start the update process by starting the updated binary. And this updated binary, basically in the beginning, does the same that we already saw before, verification, decompression, and setting some parameters. And after this is done, what we can see is that the enclave holds and waits for a signal to continue with the actual update process. So we now start again one of our helper functions that attests the updated enclave to ensure that it is the correct software and signals the enclave to proceed with the update. And once this is done, the updated enclave signals the new enclave, the old enclave, to that there is an update pending, which is done using a file where the updated enclave provides a signature, which the old enclave will see, and then also check. And if the signature is correct, it derives a sealing key using the security monitor. So this is the key that is ephemeral and only used to encrypt state for the specific update. It then encrypts its state using this specific key and writes it to another file. And after that, it signals the updated enclave, which then reads the encrypted content from the file, queries the same key from the security monitor, and decrypts the state, and then imports it. And after that is done, we can see that the old enclave gets isolated, so it cannot receive any further input, and the new enclave is up and running. So we're now provided with a new input, and what we can see now is that we actually have not just our new input that we just provided, but also the two inputs that we provided in the previous version of the enclave. So we successfully transferred the state, and the software update was performed securely. And that's already it from my side. If you have any questions, feel free to ask.
Sorry. Thank you very much, Annika and Samira. For the great presentation and the demonstration. I don't know if there is a quick question. We have exceeded about 3 minutes. No quick question also this session, so I think we can proceed with the next presentation and keep the questions for the end. So I would like call Nada, El Kazim, and Yalan Yang from Surrey, the University of Surrey, for presenting the zero-touch onboarding for trustworthy embedded devices for the next half an hour.
Hi, good afternoon, everyone.
Good afternoon, Nada. Yalan. Great. I can see the slides. Yes, we can hear you well. Just a little bit louder, if you can.
Yes, sure.
Thank you. Thank you very much.
Good afternoon. Today my presentation is about the ENTRUST and REWIRE zero-touch secure enrollment. This presentation will be presented by me, Nada Al-Qasim, and it was prepared by me and Yalan from University of Surrey. Let me start first by defining what is a secure enrollment. So a secure enrollment is a very important process that ensures that individuals are accurately registered and authenticated in some domains like education, healthcare, finance, etc., while still ensuring that their identities can be verified and protected at any time. In this presentation, we will examine the significance of secure enrollment and present the technologies that we used with the complete design of our secure enrollment protocol. Why secure enrollment is important? So basically, secure enrollment is very important to ensure that every individual is enrolled as expected. It further prevents frauds, ensures data integrity, and enhances trust and access control within systems. Many technologies were deployed in secure enrollment, such as biometric checks, encryption methods, and secure database. The current challenges in secure enrollments can be summarized into categories. The first challenge in the current secure enrollments is that they are centralized. What I mean by centralized, it means what? Whenever the authority is issued credential for the users that are enrolled in the system, in the further stages, whenever the user has to present their credential, they have to go to the third party, which is a trusted authority, in order to authenticate that it has the sufficient documents to use some applications. The other challenge is about privacy. In some applications, the user is asked to provide attributes that are certified during enrollments. So the current challenge is whenever this kind of application needs a user to present attributes, the user has to present all of the attributes that are issued during enrollment. So we need more flexible in this case by introducing what's called the disclosing the minimum disclosure of attributes. This means I disclose only the attributes that are needed for accessing the application, and I'm not I don't want to disclose all my attributes. So identifying these challenges and also identifying the project general and security requirements. The general requirements are summarized as follows. The project needs a fine-grained access control that allows users to access systems based on their certified attributes and in a decentralized manner. We also need dynamic kind of enrollment that allows new users to get involved in or enrolled in the system. And it also allows, in case of any corruption, to revoke users or revoke their associated attributes. We're also looking for efficiency. For the security requirements, the identified security requirements in the projects are: we need integrity, we need confidentiality. Integrity is achieved by creating signatures. Confidentiality is achieved by encryption methods. This is to ensure that no modification of data or disclosure to unauthorized entities. We also need a very important requirement is that we need in the enrollment to issue attributes for the user, certifies these attributes. However, we also need to bind these attributes to the user identity, and this prevents different users from collusion attacks like sharing their attributes in order to access a certain application. We also, as I mentioned, we need selective disclosure that preserve as much as possible the user privacy. Let's start with this warm-up example that is taken from the ENTRUST project. Suppose we have a cardiologist that is working at a hospital X. This cardiologist wants to sign a letter. However, he wants to authenticate himself under these two attributes, that he is a cardiologist and he works in hospital X. He wants to publish this letter. However, he only specifies some policy saying that patients can only open this letter if they are registered at Hospital X, if they belong to the cardiology department, their age is minimum of 50, they live, for example, in London or in Oxford cities. And this policy is specified by the cardiologist. So anyone can verify that this letter comes from this cardiologist and works in Hospital X. However, not everyone can open this letter unless it satisfies this policy that is introduced by this doctor. So here in this example, we demonstrated that patient like age of 48 cannot open this letter. Patients that live in Manchester cannot open this letter, or if they are not registered at Hospital X. Even if these three patients, they collude together in order to satisfy this policy, they cannot do it, because what we require is that these attributes are binded to their identities. So this policy is, that is introduced by this cardiology in this example can be transformed into what we call access trees. So access trees are some trees that have logical gates and they can summarize the policies into access control tree. In our protocol, these the identified attributes, London, Oxford, for example, Hospital X, these are the the attributes, and for each attribute we should have the corresponding key, and these keys should be only issued by trusted authorities. So this leads us to the definition of the attribute-based encryption. So in the attribute-based encryption, we find out that this kind of protocol solves the identified challenges. We need attribute keys certified by authorities. We need also to do encryption. We need to do signing. However, we still need efficiency, meaning that we need to combine these two algorithms into a more efficient algorithm, what we call encryption. So in this example, we have a sender, we have a recipient. Here the sender writes a message, encrypt this message under some attribute keys. These keys are previously certified by trusted authority. Sign it under these keys, encrypted under some attributes, and send the ciphertext. The recipient would only be eligible to open this message if it has the corresponding keys to these identified attributes. In our case, we have the brown, the green, and the gray color. So if the corresponding keys are owned by recipient and the policy is satisfied, in this case, we can open the original message, and anyone can verify that this message is signed under this sender with these two attributes keys. So here we combine what we call attribute-based encryption and attribute-based encryption in one algorithm called attribute-based encryption. So coming back, closer look to our project. In our case, we need, for the security enrollment, we need to define some attribute, but in the content of security attributes. So here, what I mean by security attributes are some attributes that preserve security or safety. For instance, we need the device to be having authenticated traces. We need the device to be having certified, trusted computing based. For example, we need key restriction uses policies or verifiable policy informants. So these kind of attributes are certified by an entity called the Privacy CA, and these attributes can be combined into a policy or included in some policy or predicate that is needed for the devices in order to be enrolled in special domain. So let me introduce the involved entities in our secure requirement. We need the Privacy CA that certifies set of attributes. We need a device to be enrolled, and each device is identified by a unique identity key. We need a domain manager. So after being issued certified attributes or verifiable credentials, the device wants to be enrolled in special domains. Before, in this kind of domain enrollment, the device should demonstrate that it has certain attributes or it satisfies certain policies that enhance the security of the enrolled devices. And in some cases, we need also to involve the device manufacturer. This is where we are dealing with very low constraint or resources devices. So as I mentioned, the attribute keys each are issued by the authority is according to a well-defined policy. As we see before, the attribute keys are binded to the identity in order to prevent collusions. We need somehow to do encryption and signing. However, these two operations may have different policies and hence different attribute keys. So this is a very high level of the enrollment. We have the Privacy CA. So we have here the device and we have the domain manager. The device whenever the device wants to be issued some attribute keys, the device has to authenticate itself, either directly authenticate itself to the privacy CA or through the manufacturer. The device has to authenticate itself, then the privacy CA has to issue for each attribute embedded in this device an attribute key corresponding to these attributes. After this, whenever the device wants to be enrolled, it goes to the domain manager, demonstrate that it has these set of attributes that satisfy a certain policy. And this is done through the sign encryption process. And if this is successful, then the device would be enrolled in a special domain. So the onboarding, here we have the issuance of the verifiable credentials that are a set of certified attributes. This is issued by the Privacy Certification Authority. We have this, as we mentioned, this kind of issuance allows the attributes to be binded to the device's identities, and these attributes are security attributes such as secure boot, device identity, domain ID, etc. So here we have the device domain enrollment. After being issued and certified a verifiable credential, the device, as we mentioned, want to be enrolled in a specific domain. So the device sent a request to the domain manager. The domain manager then asked the privacy CA to issue an extra attribute key that is related to this special domain. And this attribute key is then signed by the domain manager under its own attributes and encrypted under some attributes that should satisfy certain policy in order to be for the message to be decrypted. This is called the sign encryption process. The encrypted message is then sent to the device. The device, if it satisfies the security policies and safety requirements, can decrypt and get the domain key that is issued and bind it to the device's identity, and uses this key at later stages to demonstrate that it belongs to this special domain. And based on this enrollment, a credential is issued by the domain manager on any other attestation keys. So let's go a little bit here into the cryptographic algorithms. I'll present it at very high level. Here we have the attribute key issuance, the onboarding, where this protocol is run by privacy CA and the high-end devices. In this case, as you see, these keys are binded to the device's identity key, that is X, and the G2 to the power X. After this, we have the domain enrollment. This is where this encryption is run between the domain manager and the device itself. The message here, the encrypted message is, as I mentioned, is the domain key that is issued during the domain enrollment. And here we have the verification. The domain key is retrieved only if the policy is satisfied and the device is in a secure position and it satisfies some security and safety requirements. And this was for the high device enrollment. The other part of my presentation is about the low-end devices. By the low-end device, I mean the devices that have very limited resources. They can do only one kind of crypto, which is symmetric type of crypto. We figured out, according to these very limited resource devices, that in ENTRUST, they are only equipped with a PUF that understand asymmetric crypto. we figured out that hashing or provide a hash-based crypto is a solution in order to prove the integrity and authenticate these devices. So what I mean by hashing is we give some input, we put it in a hash function, and this hash function will provide an output. However, this is easy way. Going opposite is a difficult way, cannot be done. So starting from the output, nobody can retrieve the inputs of the hash function. And this leads to this formal definition of a hash function. We have a hash function that should be the first property should be collision resistance, meaning if we get two inputs, it's computationally infeasible to have two inputs that have the same output. And we have the pre-image resistance. This means the one-wayness. Starting with the output, it's very difficult to find the input for the hash. Hashing function in secure enrollment. As I mentioned, these hash functions provided a solution for authenticating low-end devices due to their security requirements and the integrity they can provide. Here, I give very high-level description of the of our protocol that authenticate low-end device and enroll them in the system. So, as I mentioned before, for the low-end devices, we need to also go to the manufacturer for authenticating the low-end devices. We also assume that the manufacturer produces some one-time public keys. These one-time public keys, they can only be used one time for security reasons. And these keys are sent then to the domain manager. The domain manager then somehow create this kind of Merkle trees that bind these one-time keys into a public root key, which is here the blue node. So the leaf nodes are the one-time public keys created by the manufacturer and can be also created by the device itself using its embedded key. And going up into this tree, you will arrive to this public key that is published. So only this, the blue public key is published, which is the root of the tree. However, all these information are not published, only known by the device itself and the domain manager. So, however, whenever the device wants to do authentication, the device has to use one of these one-time public keys and create a signature, and then send this signature together with what we call an authentication path that is part of this tree, some nodes in this tree. So the verifier would then, using this kind of authentication path, can arrive and reach this blue node. If this blue node is retrieved correctly, then the device is doing well and everything is, the verifier would be convinced that these public keys, one-time public keys, are properly certified by the domain manager. And finally, this comes to my conclusion here. As I presented the secure enrollment for both low-end and high-end devices, it's this very essential process for protecting sensitive information and ensuring integrity of various systems. For REWIRE ENTRUST, we tackled the challenges that I mentioned before, and we provided a solution to enhance security and user trust. Our designs, both designs are mathematically proven in game-based model, and this confirms the security properties that we identified. Also, a formal verification is done, and this will be presented in a separate presentation. Finally, a full implementation outside the trusted execution environment is also completed, and this confirms the efficiency of our cryptographic protocols. And we come to the questions, and thank you for your attention.
very much. Nada and Yalan. Since we have 3 minutes, if someone would like to pose questions, we have the opportunity to do it now. And since, let's say, the crypto part of today's webinars has been finalized with this presentation, are there any questions from the participants? I don't see any. So I think we can proceed. Thank you very much for the presentation.
Thank you.
But I get it comprehensive, and we can continue with the next session about reinforcing conformity certificate management and enhanced privacy. The presentation will be performed from Antonios Carmeta and Jesus Garcia Rodriguez from the University of Murcia. University of Murcia is also partner from ENTRUST.
Hello, can you hear me and see me?
Hi, Jesus, yes.
Yeah, thanks.
Great.
See my screen. Right. See this one. Can you see the screen?
Yes,
Yeah.
great.
Okay. Okay, so thanks for the introduction. As you were discussing, Jesus Garcia Rodriguez from the University of Murcia. I heard the presentation with Antonios Carmeta, but I will be the one presenting today. And well, we're going to talk a bit about the conformity certificates and how we have implemented them, especially how we have looked to achieve some enhanced privacy properties in the case of, let's say, this kind of high-end IoT device now. So those that have added some more advanced capabilities. So conformity certificates for us in the ENTRUST project are basically this kind of certificates that have certified trust appraisals that have been the result of the trust attestation process. So after this attestation process, that will be introduced in other parts of the webinar, we end up with a series of trust appraisal high-level properties such as integrity, safety, and resilience that can be certified for the device, and then the device can then use to prove that it's basically being compliant with some policies that are linked to this kind of security requirements. For this project, so we focused on creating these conformity certificates aligned with the verifiable credential standard, which is a standard that is being seeing quite a lot of focus in the identity management territory, but is essentially a way to get interoperability in the way that you create verifiable information, which is exactly what we want to do in this case. So in the ENTRUST project, we will have this trust assessment framework, which will perform the attestation process, and in the end create these conformity certificates for the device or for the domain according to the achieved properties, which can then be presented to a third-party auditor, and in the end verify that this kind of attestation process has happened. In our case, we have, well, in the project, as Nala also mentioned in the last presentation, we have different implementations or instances of the protocols for high-end devices or low-end devices, because we need to create this kind of trade-offs between the efficiency and the properties that we can achieve. Apart from that, one small part is that these conformity certificates will be issued, and the issuance of these certificates will be recorded in the blockchain infrastructure in ENTRUST, which is used as this kind of backbone for the trustworthy publication of this kind of public information. And particularly, we will create this record of the issuance for traceability of the processes that are happening for the attestation, and also to allow for quite easy revocation processes. So, for this conformity certification, what do we want in the project? What kind of security properties we will need from them? So the initial one, I mean, it's quite clear. We need them to be unforgeable, so it's not must not be possible to create a forged conformity certificate as if it was generated by the trust assessment framework. But also going beyond that, it is also feasible to present a conformity certificate as if it was real. So we will see a bit more this distinction in the next slides. Apart from that, we want to have the conformity certificate bound to the device, to the TCP, and in particular to the state of the attestation or the security state of the device. Apart then, we have the nice additional goal, I would say, of achieving selective disclosure of the properties that are included in the conformity certificate, so that we can present this kind of certificates in a way that we preserve the privacy of the security properties that the device will have. So we are hiding this kind of information from the third-party auditor and revealing only the strictly necessary information for the, let's say, proving process. And lastly, this kind of conformity certificates should be revoked when they are no longer relevant, and this means having some expiration. So we need to give them, renew them after some time with new attestation processes. But also, if an attestation process is happening and we notice that the state is not consistent with the latest conformity certificate that was issued, and we need to revoke it to avoid this kind of not reality for the presented conformity certificate. So in the Entrust project, focusing a bit more in the scenario that we have in the project, we will have these three entities: the risk assessment framework, the CMD, so the device, and the third-party verifier of it, which can be any entity in the domain. It could be, for example, the domain manager when it's requesting some information from the device. The high-level flow for this kind of certificates is, well, first, there's an attestation process, and this results in some appraisals for the device. Then we go into the phase one, where we issue a conformity certificate. Basically, the DAF will create a signature over this verifiable credential, which contains the information about the conformity certificate, will register the issuance process in the DLT and the blockchain, and will send the verifiable credential to the CMD that will store it for later use in the phase two, which in this case is the phase for presenting a conformity certificate to a third party. So a verifier requests the conformity certificate according to a policy that he wants to check from the device. For example, that the device is properly fulfilling right now the integrity requirements. Then the device needs to create a proof of possession of a conformity certificate that fulfills this policy, and potentially creating this proof, the device will not do some derivation of the new verifiable credential. And then this verifiable credential will be sent to the verifier, and in the end will be verified and checked that the policy is fulfilled and everything is as was expected. So for the instantiation of this generic flow for low-end devices, same as Nada was mentioning, in this case for Entrust, we consider low-end devices that can only do basically symmetric cryptographic operations. So for this one, we forego any privacy requirements, and we basically just create a signature, a plain one traditional signature for creating the conformity certificate, bounding the result to, of course, the identity of the device through this, for example, this path-based TCP. Then during presentation, we just reveal the whole verifiable credential that was signed, and the device proves ownership of the conformity certificate through a signature. In this case, be, for example, the same method that I mentioned before with the Merkle RISC. So in the end, we just basically need a signature of that using the keys that are controlled by the device to just prove that this verifiable credential was presented by the proper device. So for high-end devices, which is a bit where we have focused a bit more in the project from the University of Murcia, we will instantiate the process using privacy-preserving attribute-based credentials, which are also known as anonymous credentials, or we usually call PAVCs. So now the issuer generates the verifiable credential by signing it in the usual way, but now instead of just presenting it, we will generate the right version using zero-knowledge proofs. So instead of revealing the current credential with zero-knowledge proof, and we can reveal a subset of attributes and maybe some other properties. We, of course, we want to keep device binding, and we are taking advantage of the rest of the developments created in the project. So we will link this conformity certificate to the attestation key of the device. So when presented, we also need to prove possession of this attestation key. And lastly, all of these cryptographic operations will be implemented inside the DE or in the trusted computation of the device, so that we can be a bit more sure of the trustworthiness of the software execution that we create. So moving over a bit quickly, to take too much time here, PAVCs are basically a signature scheme that lets you sign a set of messages. So in this case, messages for us are these security properties that have been, or these high-level trust appraisals that have been the result of the attestation process. From these signatures, it is possible to efficiently derive zero-knowledge proofs over the signature that provide this selected disclosure, linkability, and some predicates over attributes. In this case, in the project, we don't really need that much. We are completely fine with just selected disclosure because of the requirements that we need for the conformity certificates. Apart from that, as we wanted to go into verifiable credentials, we have to say that the PAVCs are quite aligned with this specification, and basically you can just generate a verifiable credential that has been proved through the PAVC signature, and when we go into the device, we can just modify the contents of the verifiable credential and create a new zero-knowledge proof over the signature that is will be linked to this new derived verifiable credential. So in the end, you you get this reduced information sharing in the process. An example of this, but I will go over a small demo after this, so I think we will see it better there. But you get the original credential with all the information, and in the end you can derive a new credential with reduced information and with a signature proof instead of a original signature, basically. For the cryptographic protocol, in this case for the high-end devices, quite simple at least from the abstract point of view. We can go into more details later on if there are some questions, but in the end, what we will have is that the TAF gets the attributes that needs to sign, including particularly the public part of the attestation key of the device. So all of these attributes are signed using the signature algorithm of the PAVC scheme that we use, and everything is basically wrapped in this verifiable credential that is sent to the device to be stored in the DE for later use. Then, when we go into the presentation process, we get a policy from the third-party auditor, and the device parses the policy to check which attributes are requested and will be revealed. So from the stored verifiable credential and signature, we perform a zero-knowledge proof. So we derive this new proof over the revealed information. We serialize this as part of a new verifiable credential that contains the reused information, and we sign everything with this attestation key. So the specifics for the attestation key signing can be or will be explained in a little presentation by my colleagues by UBITECH. In the end, the a third-party auditor can verify first the signature of the attestation key, then the validity of the zero-knowledge proof, and then that the verifiable credential that was presented fulfills really the policy that was requested. For example, as I mentioned before, that integrity check was passed during the attestation. So in terms of an implementation, I will, I think, go a bit quickly over this, as I will show the, let's say, leave in the demo, but basically we have in the server side, in the TAF, we have an issuer that is implemented basically using a general purpose SSI wallet, which is based on ABS basically, but we modified to include this cryptographic algorithm, the PVC scheme. And we use basically we use this because we saw that this is actually fully compliant with this kind of self-sovereign identity procedures based on verifiable credentials that are basically becoming a standard right now in this part of the community. Then we have in the device, following the strategy, let's say, of the rest of the project, we have the main part in the trusted execution environment, which will include this trusted computer base of the device. We have a trusted application for the PVC cryptographic operations. This trusted application, we have implemented it within OptE following this global platform API, so it should be quite easy to port to other solutions. And we have then, of course, the executables in the normal world, so outside the DE, that will interact with the trusted application. Then we have this, let's say, Python part of the code that is used for the, let's say, management of the flow. So we get a server for communication with the outside world from the device, and here basically we are following the, let's say, the general approach for integration in the project, but it's not a, let's say, hard requirement on the implementation. It could be using other languages. It could be using gRPC communication instead of HTTP. But we are basically using this one for the, let's say, proof of concept that we're doing in the technical. So for the demo that I will do, I think I'm quite fine on time. We are running this on the high-end device that we are using in the project because of the use cases, which is a Raspberry Pi 3 Model D, which has been flashed with an OptE image that has the trusted application that we created and this reduced Linux kernel on top of that. We use 7 attributes. I will show the credentials that are generated in the end. We will see the structure, and I will go into the demo, but before that we had some benchmark already on this implementation, and for the server side there's not much of an issue, as we're basically using a common purpose computer, but in the end some ballpark could be around 50 milliseconds for the whole execution. Then during the issuance, as we store things in the trusted world, we will create this context for the trusted application, and in the end this takes around 0.54 seconds. And for derivation, we have a load time for around 1 second, where the crypto operations are around 0.3 seconds, which is quite manageable. And then we have the processing for the JSON, and then especially the context switching to the trusted world and so on, which take at least a bit more, 0.5 seconds, including everything. So I think for the presentation, I think that's enough. I will take it down here and start with the demonstration. I think you can see the screen perfectly fine. Yeah. Okay. So the setup, as I was mentioning, is basically it's quite simple. We have a computer here, and then we have here the Raspberry Pi, which is connected through Ethernet, and then I have here 2 terminals that I already logged into the computer through SSH here and through the Raspberry Pi again through SSH. So the first part of the demo is executing the issuance process. So we can we basically created some Python scripts just to okay. Sorry, I need to start the device. Okay, I wanted to use only these ones, but first part, let's go into the device. We need to prepare the device for the execution of the demo. Sorry about the mix-up. And for this, we have an init sh execution executable, which will start the Python server that I was mentioning before, or listening to the communications with the server side and to any entity outside the device. Apart from that, this script is getting some public information that will be needed during the execution, basically the ID, or particularly the public key of the issuer, and some information about the normalized or digest of the JSON verifiable credential that will be sent to the device. Now, now that the device is listening to the calls, we can start the issuance process. And here, basically what is happening is that we, from this script, we call the issuer, so this SSI wallet that I was mentioning, we get the verifiable credential and send it to the device that stores it internally. So the verifiable credential that we get in this process is presented here in the logs. And basically, we are showcasing some example attributes that we are not including the tab here as of yet. Basically, they will be coming from there. And a couple examples that the availability check for the device is achieved, so we get a no, but then for integrity we get a yes, for resilience we get a yes, robustness yes, and safety also yes. And then we have the public key, to which the conformity certificate is basically bound, and a revocation handler, which is basically an identifier where we then later on in the list in the blockchain we can have this list of revoked conformity certificates, so that it's easy to check whether this identifier is there or not, and to check the revocation status. Apart from that, then we get this proof, which is basically the one that provides the verifiability for the verifiable credentials, and it's created using our, let's say, signature suite, this PSMS PLS signature 2022 that we created. And here, basically, we have the signature or serialized signature for the PVC scheme. So after this process, here we have some additional logs for the verification. So the device basically verifies the received verifiable credential and signature is fine. And after this process, we basically finalize phase one. So we have the device with the stored credential that is ready for to be presented according to any policy that is requested from the device. So for this part, then we using the same computer just to avoid having a more complex setup, which could be anyone else. We create another script that requests a conformity certificate according to our policy. So basically, we execute the script. We're getting quite a lot of information here, but basically we have first in the book, we requested the presentation of a conformity certificate according to this policy. So it's an announce. So the announce is basically something that ensures the freshness of the presentation that was generated for the policy. And then we request a series of disclosed attributes. So integrity, also the public key, just to check the binding for the device, and the revocation handler, as we want to check the revocation status of the credentials. Then after some time, here we have the full logs of everything that happened, but in the end, the application is now returning right now the derived verifiable credential. So the device verifiable credential, it's appearing twice, but basically we see that we have the credential subject here. Now instead of showing everything, we only have the integrity, public key, and revocation handler attributes. And in the proof field, we actually now have a PSMS PLS signature proof. So basically, synchronized proof with a PSMS PLS signature. And the proof value is here, which is different from the one that we had before, and it's actually longer because of how the PVC works. So this shows that things are working fine, and actually what we can do, for example, here is for the request CC script, which is quite simple. We just basically call the API for the device for to present a conformity certificate. So it's not something very simple, but we can add a different attribute here. For example, that was not requested before. We can make a safety here, and if we execute the flow again, we will get a verifiable credential that again has the integrity, public key, revision handle, and then the safety also is good. So basically, this way we can play around with the kind of information that is revealed during the presentation process. Some, I guess, could be more or less interesting parts of the code. I think that the most important part is, or at least the most interesting part, as the other basically glue for integration, is the PVC trusted application and the client applications that are used to make it with it. So we basically have here, I brought it out from the OPTI environment. It was easier to see, and basically we have a trusted application that provides the entry points for different interesting algorithms or protocols from the PVC system. So from generating a key to reading the public key for the private key that we are storing right now in the device, to creating a signature and storing the signature also. So in the flow that I have shown before, we actually use the zero noise token generation from the store signature and the signature storing and verifying commands. So we have those in the flow, but we could use every part of the cryptographic algorithms from the PVC can be used during the whole setup. If we want to have the device, for example, generate its own type of credentials. In the case of Entrust, then this is not necessary, but the use case is possible. Then from the basically from the other part, from the client side client application. So in the normal world, we will call these operations basically further along the process of the conformity certification. For example, here is the operations for the generating a zero noise token from the policy. So we actually get this use this global platform API for passing the arguments with the PEC parameters. We have the PEC call and the invocation command. So here, all these codes will be public, so everyone can check whatever they want about it. We have this, let's say, core part of the cryptographic operations, and then in the Python scripts, we, for example, those over here is Flask and API. We basically have the, let's say, a bit more abstract layer that is used to glue everything together into the device, the trusted computing base of Entrust, and this overall operation of the different parts of the project. So I think it's here now, and basically I think I will be a bit ahead of schedule, so a couple minutes. But from my side, I think I showed the main parts that are there, and also the demo. But I'm open for any kind of question or any kind of comments that some things want me to talk a bit more in detail for. Thank you.
Yes, great. Thank you very much, Jesus. Congratulations for the presentation and the demo. Now I can give the floor for questions. We have 4 minutes ahead. before we proceed with the two last sessions going to be performed by UBITECH. If there are any questions, please raise your hands to be able to see you and give you the floor. No questions. Thank you very much, Jesus. And let me give the floor for the next presentation. The floor goes to Giorgos Pekridis, Nikos Favritsiotis and Stefanos Vassiliadis from UBITECH for the efficient scalable attestation mechanism for RISC-V devices.
Hello everyone. Really nice to give you this talk today. I'm here with my colleague Nikos and of course Giorgos. So let me share my screen here. Can you see my screen?
Yes, great.
Okay. So for this presentation, I'm going to present you the configuration integrated verification that was designed for the REWIRE EU project. Taking a step back, REWIRE is built on top of strong trust guarantees to fortify the security of IoT devices, edge devices with hardware-backed security. For the REWIRE project specifically, we have chosen RISC-V open hardware architecture, where we use a trust execution environment called Keystone. This is actually one of the most mature trust execution environments for this specific architecture. We have also experimented with some others like Penglai, but eventually this was our design choice because of the maturity and how much was spread in the RISC-V community. And in order to actually complete the design of our configuration integrated verification scheme, what we did is that we emulated the concept of trust device interfaces, TDIs. So for this purpose, we have defined 4 different trust device interfaces, one dedicated for a specific security mechanism that is exposed from each device that is participating to the REWIRE infrastructure. So the first one is of course the key management that creates keys and basically creates a secure environment when we can securely derive attestation keys. We have enhanced authorization mechanisms and key restriction usage policy verifiability, where we restrict the access of these attestation keys from malicious usage, and key restriction usage verifiability, where we attest the static and dynamic attributes of the devices. And finally, we have a TDI dedicated for tracing, where basically we introspect properties of the system or binaries that are running inside the device in order to check whether they are running as they were supposed to. So taking a deeper look inside our configuration integrity verification scheme, we have basically 3 participating devices: the domain manager, which is a trust third party, the prover, which is an edge device, and the verifier, which is basically agnostic. It can be a trusted third party as well. It can be another device that is onboarded on the REWIRE infrastructure, or it can even be a compromised device because of the privacy-preserving nature of our scheme. Basically, what I mean by that is that even if the verifier is compromised, he can't actually extract any information regarding what's running in the prover side from an attestation code. So the domain manager specifically what it does is that he onboards each device that wishes to participate in the REWIRE infrastructure by attesting its trust computing base, and then issues the key restriction usage policies under which the prover can construct a valid signature. So inside the prover, as you can see, there are three components that instantiates the REWIRE TCB. We have the attestation agent, which basically invokes the trust device interfaces for key creation and authorization. We have the verifiable policy enforcer, which uplifts the security of the device to from plain key restriction usage policy to a verifiable key restriction usage policy, attesting all the static properties, static attributes of the system prior to enabling the usage of the key. And finally, the tracer, which is basically again a protected application which introspects the runtime properties of the system or specific binaries that we wish to attest. So the design behind the REWIRE attestation engine was to ensure the secure life cycle, the entire secure life cycle of the device. This was done under the sense of trust assessment. We needed a way to assess the trust level of each device that is participating to the REWIRE infrastructure in a verifiable manner. So for this purpose, the main motivation was behind the integrity, trust property of each participating device, and we wanted to assure resilient, robust, and safe mechanisms that can characterize a device as trusted. So for this purpose, we have design time integrity, where design time is the offline period of the device, where each and every application that instantiates the trust computing base of an REWIRE-enabled edge device is formally verified. Boot up integrity, where we employ well-known attestation mechanisms like secure boot that assures that everything was launched and booted correctly. And finally, runtime integrity, where we leverage the key restriction usage policies and, of course, the tracing capabilities of a Unix-based system to attest the validity, the integrity of the running binaries and properties. So the last part, and which was our biggest innovation, was again the zero knowledge nature of our scheme that protects against implementation disclosure attacks, where we were enabled to provide attestation evidence without disclosing any information of what is running inside our device. Apart from that, we also protect against rollback attacks and replay attacks through leveraging challenge-based attestation mechanisms and, of course, key restriction usage policy verifiability, and as it was a really critical property for our design for the REWIRE infrastructure, we support the secure execution of software updates, as it was shown in the previous demo as well. So taking a step back, just to clarify again how the REWIRE configuration integrity verification scheme enhances and makes everything better for the secure life cycle of an edge device. So we went from like runtime attestation, where we have there is many research in the literature, to uplifting this with tracing capabilities, real-time introspection without posing any performance overhead. Like we employ a tracer, as we say, it's like a silent observer that runs inside the secure world and introspects what's happening inside the device. And of course, we have safety zones, because everything is protected by the physical memory protection layer of the RISC-V architecture, and is formally verified that it doesn't have like major vulnerabilities, because of course no software, either it's running in the secure world or not, can have zero vulnerabilities. And of course, the biggest innovation, as I said before, was local attestation, as we enabled the scheme to run in a zero knowledge manner, avoiding attacks such as implementation disclosure attacks, where an attacker can observe what's been reported over the network and can find vulnerabilities, known vulnerabilities to the attested binaries. So let's take a deeper dive to the REWIRE attestation scheme. First of all, each device, as I said, has to be onboarded in a verifiable manner to the domain manager. So the attestation agent creates the attestation keeper and sends its public key to the domain manager. The domain manager then computes the key restriction usage policy that contains the static properties that characterizes the device's trust computing base, and creates, of course, the VPE key. The VPE key is binded with a policy that depicts the static properties, static attributes of the trust computing base of the now enrolled device. When this is done, the domain manager creates an authorization ticket for the attestation agent, which is a representation of the dynamic attributes of the device. So these are sent back to the device, and in a trusted manner, like they are encrypted with the root key of the device, protected by a secure and authenticated communication channel, etc. And then they are consumed by each component accordingly. The VPE gets his key, and the attestation agent gets his authorization ticket. Upon these actions, now the device can act as a standalone component, and no interference from a trusted party is needed. So during runtime, what happens is that the AA gets challenged to produce an attestation report. So to start this procedure, the AA sends to the VPE a challenge, and the VPE on his own terms sends a challenge to the tracer. The tracer now starts introspecting the binary or the system properties that was defined under a policy during the design time, that was characterized vulnerable or critical by the manufacturer or the service provider, and sends the traces signed to the verifiable policy enforcer components, along with a signature that depicts his own static attributes. So the VP now will go and verify first the static attributes that characterizes the tracer. He will then attest the static attributes that characterizes the attestation agent, and he will send the ticket to the attestation agent that says that, okay, these are the traces that are valid and the tracer is valid, and also you can unlock this ticket only if you are in a correct condition, which means that only if you actually have the static attributes that I have defined. So the attestation agent now receives the traces, receives the ticket from the VP, and goes on to use the trusted device interface for key restriction usage policy enforcement to check whether or not he satisfies, first of all, the correct configuration, the static attributes of the attestation agent as the domain manager has defined, and has to verify that the traces that were received from the tracer are the ones, the golden hashes that were defined by the domain manager as well. If these regulations are all satisfied, then the attestation agent can actually use his key to produce a valid digital signature, an attestation report, and this is returned to the verifier, to the device that challenged originally the prover. So for our implementation, what we did is we developed our scheme using Keystone, of course, and we actually managed to configure it to run in two different platforms. One in Xilinx Kintex Genesis 2 board, which it's an FPGA board that was configured to run a CVA 6 core, and the other one was a Star 5 Vision 5.2 board, which is basically like a Raspberry Pi with RISC-V architecture, which is quite powerful. So that's it from my side. I will leave the floor to my colleague Nikos to demonstrate the whole flow of our scheme in the Vision 2 board.
Hello from my side. I hope you can hear me and also see my screen. So, picking off where Stefanos left it, we shall now see the execution of the CIV scheme on the Star 5 Vision 5.2 board, which is what is currently running on the screens you probably see on your screen. So, as you can see here, we have 5 terminals. Those 5 terminals are the first one on the upper left corner is the one controlling the whole scheme. It's actually like an orchestrator which initiates the CIV scheme. The second one right here is the attestation agent, which is responsible for the creation, the management of the attestation key and the signing of the report. The lower left terminal is the terminal that handles the VP, the verifiable policy enforcer. This terminal right here is a dummy tracer which creates the traces that are going to be verified against the expected traces and are also going to be sent to the attestation agent, so then it can use its own attestation key. And this final one is the domain manager. Now, the domain manager, which is responsible for the creation of the policies, of the credentials, and the creation of the attestation keys, probably in a real case scenario runs outside of the device in a trusted third party. But for the purpose of this demonstration, we're going to also run this on the device. It does not really affect the execution of the whole flow. What is also worth mentioning is that this scheme currently has two trusted applications, the attestation agent and the VP, actually run in an enclave, thus utilizing the capabilities of the Keystone and RISC-V platform to maximize the trust of the scheme. But for the purposes of this demo, these are also going to be applications in the normal world. But we have, as we have already written in the deliverable, they have also been benchmarked as trust applications. So let's start the execution by running what I mentioned before as the orchestrator. Now, after we run, we have three applications, three modes of execution set up. The first one is the join stage, which is what Stefanos previously described as the enrollment of the device. The runtime stage, which is the actual operation we might do more often during execution to whenever a verifier asks the device to prove its integrity. And the final one is the software update that I think already Annika has demonstrated before. So let's try to run the join phase. As you can see, we have things running here. And let's try to briefly explain them one by one so that it is more clear what the device actually does. So the attestation agent starts by sending its root ID public key and its attestation key name to the domain manager. Now, whenever I say that one application sends something to another application, that always means that everything goes through our orchestrator, our helper client. So the attestation agent sets its root ID public key and the attestation key name to the helper client, which in turn sends those two things to the domain manager. Now, the domain manager then sends the credential, the authorization digests and encrypted random secrets and the IV for the IS encryption back to the helper client after it has created those things. And those are actually sent back to the attestation agent. It then proceeds to now the attestation issuer verifies the state of the device. It sends the attestation credential back to the domain manager, and now the VP will now verify the signature of the domain manager. So this is the verify state that we are mentioning right here. And after the VP verifies this credential, it then sends back to the attestation agent the join phase stops. So after all these steps, the enrollment of the device into the network is done, and we are now ready to execute the runtime phase, which again is run whenever a verifier requests for the device to prove its integrity during runtime. So let's start our client again, and this time we're going to run runtime. So in order to be able to run the runtime execution phase, we must first have already created our attestation keys and have enrolled into our network. In practical terms, before running runtime, we have to at least run once the join phase into the same session. So running the runtime, we now have things running in all of our applications, as you can see here. And let's try to examine those log messages a bit more closely. So when a verifier requests runtime evidence, they first send the challenge to the policy orchestrator, or in this time, the helper client. Now, the helper client notifies the tracer to begin its runtime function, as you can see here. The tracer produces the device runtime traces and signs them with its own private key. After that, the traces are sent back to the helper client, right here, and in turn forwards them to the VP, as you can see right here. The VP then essentially ensures that these traces come from an authenticated tracer and that the attestation agent practically has not been compromised. Then the tracer authorizes the attestation agent to check the validity of those traces against their predefined policy. By doing that, if and only if the attestation agent has confirmed that the device is at a valid state, the attestation agent can sign the verifier challenge with its attestation key. After the creation of the signature, which you can see here, after we have already proven that neither the tracer is compromised, neither the attestation agent is compromised by running multiple policies or something, then the attestation agent checks that the traces are valid and are correct and are also the expected traces against comparing them against to the predefined ones. Then the attestation agent can actually use its attestation key, has completely recreated the correct attestation key, and can now use this key to be able to sign the nonce that has been sent to the helper client via an external verifier. And as you can see here, we now send back to the server the signature signed with our private attestation key on top of the nonce sent by the verifier. And here is that signature. Here is that signature. Those evidences, the evidence R and evidence S, which are in line with the format of electrical key signatures. And we now send this back to the verifier, and this is pretty much the whole of the flow. So I think we have successfully demonstrated a correct execution of the CAV on our Star5 Vision 5.2 platform. This is actually running on the actual device. And yes, open for any questions you might have.
Nikos, thank you very much, Stefania, as well for the presentation and the demonstration. I don't know if there are any questions from the participants. I don't see any. So let's proceed with the last session that we have, and leave space also in the last for the Q&A session. Nikos Fotos from UBITECH is going to present the Dynamic Trust Assessment Framework. You also have 6 minutes extra from the previous sessions.
Great, thanks a lot, Thanassis.
The floor is
yours.
A lot.
Yes, thanks a lot. So, thanks everyone for attending this seminar, this webinar. Actually, this is the final and concluding presentation, and hopefully, with this presentation, we will be able to connect all the dots that we have presented today. And of course, we have seen across the webinar different mechanisms that enable assessing the trustworthiness of a device, both during the onboarding phase. So what are the assurances that we need to have in order to onboard a new device in our topology, but also ensure that these guarantees are also kept and maintained during the operational phase of the topology. And basically, the trust assessment framework sits in the middle of this process. And yes, at the beginning, think of our trust assessment framework as a black box that takes as an input a set of evidence. And we've seen the different attestation metrics previously, or even the misbehavior detection elements from the previous webinar on this past Friday. So it collects a set of evidence, and eventually the trust assessment framework, or the TAF in short, outputs a so-called actual trust level. So based on a set of evidence and weights and different calculation mechanisms, it provides an assessment on whether a device or a piece of data can be deemed trustworthy or not. So by looking at today's agenda, first of all, and this is basically, think of it as an exercise, and in order to see how the trust assessment fits in each and every of the discussions that we had today. So in the first presentation, we had the discussion about securing the software and firmware update process. And basically, at that point, the trust assessment framework can provide a score or a trust characterization on whether we have provisioned the correct cryptographic keys in order to carry out such an enhanced cryptographic mechanism to ensure that our software and firmware update process is well secured. So we need evidence in order to have our trust assessment framework to deem whether this process can be deemed as trustworthy or not. Then moving on, we have seen how we can carry out a software update process, a secure software update process. And from the trust assessment perspective, from the trust assessment perspective, this can be considered as a control in the sense that when the TAF detects a low ATL, so a low trust score, then our domain manager or our framework could use a software update process to patch a vulnerability or an existing threat. And this would allow eventually for the trust assessment to re-evaluate the system and deem it trustworthy again. And moving on. Of course, we discussed about the onboarding phase of a device. And as we have already discussed, the trust assessment framework could basically unlock such an onboarding framework in the sense that we could consider a domain manager or the enrollment orchestration part that waits for the trust assessment to deem a device as trustworthy before onboarding it to the topology. And then, of course, the conformity certificate part presented by Jesus earlier on, this is an essential way to convey the trust assessment results to a relying party or to any interested party. So when the trust assessment framework decides that a device can be deemed trustworthy in terms of integrity, then this can be conveyed, this assessment can be conveyed to any interested party in the form of conformity certificates. And last but not least, we have seen the attestation. Yes, we have seen the attestation mechanisms. And in the context of the trust assessment framework and concepts, the attestation mechanisms constitute an important and a crucial trust source, or source of trustworthiness evidence, because it allows the trust assessment framework to securely collect and verify guarantees about system properties of a device, such as the integrity or the resilience of the device. Okay, so let's move to a bit to the inner world of the trust assessment framework. So in terms of requirements, we want our black box, as we mentioned it at the beginning, we want our trust assessment framework to be dynamic, both in terms of the evidence that it collects. So remember that we need to collect evidence during runtime in a continuous manner, but at the same time, we want our trust assessment framework to be able to react to changes in the topology. So what happens if a new device gets onboarded in the topology, or what happens if a device gets disconnected or detached from the topology? So we need our TAF component to be able to react in that kind of dynamic nature or dynamic environments. At the same time, we want our TAF output, so our trust assessment, to be derived from fresh and securely collected evidence. So we want an evidence-based output that will allow us to move from a set of attestation results and misbehavior reports to a concrete trustworthiness decision. And of course, one critical point is that we need to be able to cope with uncertainty, because it is clear that there are different trust sources that could provide evidence with full certainty. So for instance, let's consider the case of secure boot. So if we have the certificate chain that proves that all the target measurements are correct, then we are sure 100% that we have secure boot in a system. But there are other types of evidence that could potentially raise a flag or a misbehavior detection with a level of uncertainty. So we need to be able to cope with these different kinds of trust sources. And yes, when we consider different and more complex topologies where different nodes provide assessments from one to another, then we need to consider reputation-based requirements and capabilities. So what happens if one device assesses its adjacent neighbors? So this is the term here, multi-agent systems, in the bottom left corner. And of course, in that kind of complex topologies in multi-agent systems, we might have different nodes assessing a target node, but with different, let's say, opinions. So what happens if two neighboring nodes have a contradicting assessment for a target node? Then in that sense, the trust assessment framework should be able to derive one, let's say, common and aggregated value, taking into consideration all this conflicting evidence. And last but not least, we need our trust assessment framework to have context awareness, in the sense that, first of all, we can consider that trust is subjective, so an entity might have different requirements and different requirements for evidence in order to deem a device as trustworthy. So in a domain, we might only need the secure boot evidence in order to enroll, for instance, a device. But in another domain, in a more strict environment, we might have different types of evidence that could potentially deem a device as non-trustworthy. And then in that sense, we need our trust assessment to be able to express and cater the needs of different domains at the same time. So this is why we highlight the need for context awareness. Okay, so moving on, I will try to spend 3 to 5 minutes to give a quick overview of some common terms that we will be using throughout the demo and this presentation. So, okay, first of all, we have already mentioned quite sometimes in this webinar the whole concept of security property. So think of it as different properties that characterize a device in this context, in the context of REWIRE and ENTRUST. So this could be, for example, integrity and resilience of a device, or a specific portion of a device. And this is our security property in the terms of the trust assessment. And then we have the trust object, which of course it is, think of it as the device that we want to assess its trustworthiness. So for instance, a device with a specific ID is our particular trust object for the assessment. And then, given these two terms, the security property and the trust object, we can derive different trust propositions. So statements that we want to assess their integrity, their trustworthiness. So for instance, we could have different queries being fed to the trust assessment framework, such as, I, as an assessor, I want to evaluate the trustworthiness of a specific device in terms of integrity. So this could be a trust proposition, a simple trust proposition, which we denoted here in the example as X. But at the same time, we might have different types of trust propositions, such as the resilience, or we could go even one step further and go more specific to our propositions and maybe define assessing the trustworthiness of a device with respect to having secure boot. And with this way, we could, what I'm trying to convey is that we would fine-grain our trust propositions as detailed as we can. And of course, this is dependent on the type of evidence that we can collect from our operational environment. Then, given the trust propositions, of course, we have other terms such as the trust relationships and the trust opinions. And these basically allow us to map a set of evidence to specific trust propositions. So again, in the example of having a trust proposition such as device 1 has secure boot, then by collecting evidence about the secure boot of the device, I could map this evidence to a trust opinion on this proposition. And this is basically the terms relationship and opinion. Basically, they allow us to design a graph or a model where we have multiple trust relationships and multiple trust propositions. And we could have we could go as complex as we want in terms of the trust assessment modeling. And then, as we have already mentioned in the introduction, we have the trustworthiness evidence, all the bits and the secure pieces of data that we can collect from the operational environment that will allow us to derive trust opinion and the trust assessment, and eventually we have the actual trust level. So this is the final output of a trust assessment process. And as an example here, as I mentioned, the goal is to map this a device topology into a set of trust objects and trust relationships and trust propositions, depending on what we want to assess and eventually what we want to include in our conformity certificate. So, for instance, this is an example where we have the root node being our assessor. So, so who is the one that wants to assess the device integrity, for instance, and then we have different trust relationships towards the statements that we want to assess. For instance, here we have the X as our trust proposition. And even though we can go as fine-grained as we can, at the same time, we can define complex combinations of different trust propositions. For instance, I want to assess one trust score related to the device one having integrity and resilience. So you can see that we can combine different Boolean or logical expressions between the trust propositions. So yes, I tried to squeeze all these terms in a couple of minutes, but then let's see the internal architecture, at least in a high level, of how the TAF looks like. So first of all, let me go back. We can define there is a single term that characterizes this kind of graphs, and this is called the trust model. And basically the trust model consolidates all this information as of who assesses and which type of statements does this root node want to assess. Okay, so we have this kind of three major boxes inside the TAF. On the right-hand side, we have the trust source manager here, and this basically collects or interacts with all the different probes that we have in the operational environment. For instance, one trust source could be the attestation agent that Nikos and Stefanos mentioned earlier, and basically the TAF would ask for specific set of attestation reports and claims regarding some security properties of a specific device. But we even discussed this past Friday that we could also have misbehavior detection probes in the operational environment that could potentially detect some abnormal behavior. And this could be also consumed by our trust source manager. And then the question is how this evidence, this JSON and this encodings of evidence and security claims can be converted to trust opinions. So how we can move to the realm of the trust assessment framework. So basically this is the idea or the goal of the trust source manager, that we will try to map all the pieces of evidence to specific scores, characterizing the belief that we have over a trust proposition and the uncertainty that we have at the same time. So for instance, based on some contradicting evidence, this omega value, which is the trust opinion, could be I trust that the device one has integrity with a belief of 0.8, so think of it as a probability, but I also leave some space of uncertainty of 0.2. So this conversion from evidence to trust opinions is carried out by the trust source manager. And of course, this trust opinion is persisted on our trust model manager, which keeps track of the entire graph of trust relationships and trust propositions. Now, the trust model instance in this case is fed to the third box in this layout, which is called the trustworthiness level expression engine. And depending on the target trust proposition that we want to assess, so in this example, we want to assess the integrity of a specific device, then this TLE engine, the trustworthiness level expression engine, will take the trust model instance, so all the opinions and the specific propositions, the leaf nodes that we want to assess, and will provide an actual trust level. And to do that, in the context of ENTRUST, where we design and implement the trust assessment framework, we adopt the notion of subjective logic operations. So we we fuse and aggregate all the different trust opinions in order to derive a final score, which is the ATL for a specific trust proposition, for instance, integrity. And now we have a score, consider it or think of it from 0 to 100, but then of course we have a score that might be of some importance to an end user, but at the same time we want to derive a trust decision based on a threshold value that we want to define. So maybe in some cases, as we will see in the demo, we are not interested only in the nominal score 0 to 100, but we are also interested in the final outcome. So whether the device can be trusted in terms of integrity, and to achieve this, to realize it, we need to provide a so-called required trust level. So what is the logic and the thresholds that needs to be included in our trust decision process in order to derive a final outcome? So, and the outcome is basically a true or false value. So whether I can consider a device as trusted or not for a specific trust proposition. Okay, so this is the main idea of the internal layout. Now, before moving to the demo, some details about the implementation stack that we have used. So, yes, and again, this trust assessment framework that we have used in the context of ENTRUST is basically a continuation of an existing trust assessment implementation that is coming from previous projects as well. But the idea is that we have adopted the source code and we have tailored it to the lifecycle management of the device framework that we have in ENTRUST, and could be also applied also in the REWIRE concept. So for this trust assessment framework, the main implementation of all the internal components and bits and interactions is in Go. And basically this allows all the interactions for different sessions and different parallel processes to take out to be carried out rather efficiently. So all the communications between the trust model manager and the TLE and the trust source manager is carried out basically using Go routines. And now, in order to interact with the trust assessment framework, as we will see also in the demo, we have used an Apache Kafka broker. So think of it as the TAF basically listening to a specific topic or queue, and then each entity that wants to interact with the trust assessment framework, for instance, in order to perform some queries about the trustworthiness of the device, they basically have to develop their own Kafka client in order to send a set of requests to the trust assessment framework. Now, the interesting thing is that the trust source manager, as we saw in the previous slide, interacts with one or more trust sources, right? And then this communication can be either carried out via Kafka channels, so dedicated topics where each trust source can send messages. But then we have also, in the context of ENTRUST, we have also developed and extended this functionality with REST APIs. So as we've seen in the previous demo, the attestation agent, so the orchestrator, can be reached out via REST HTTP calls. And then the trust source manager, depending on the trust model that we want to assess, it basically reaches out to the attestation agent in order to get fresh evidence. So what I'm trying to highlight here is that the trust source manager can be extended in different ways in order to accommodate for all the implementation specifics of its trust source. And this gives some merits to the trust assessment framework in the sense that it can be extendable with tons of trust sources depending on the requirements of its use case. Okay, so let us go to the demo. And for this demo, for today's short demo, we will use one of the use case scenarios of the ENTRUST project. And basically we will focus on the use case where we have a smart ambulance that carries out a patient towards a hospital. And during this process, during the process of carrying out the patient to the hospital, there needs to be a trustworthy transmission of data from the smart ambulance topology, so all the different sensors and actuators giving critical information such as blood pressure, different metrics for the patient, and reports them to the hospital administrative domain. And then at the same time, we want to collect attestation evidence about the smart ambulance topology and other metrics that will allow us to provide guarantees about the correctness or the trustworthiness of the devices participating in this interaction. And to provide a slightly more detailed figure, we can also use this kind of layout where we have different sensors here at this level, and these sensors refer to sensors deployed in the smart ambulance topology, and these sensors communicate through a gateway device, a high-end device, to the backend application to provide this critical patient data. But at the same time, they provide attestation reports and evidence from the operational environment of the smart ambulance topology, and reports them in a privacy-preserving manner to our trust assessment framework. And then, from the backend application of the hospital side, basically the backend application can query the trust assessment framework in order to check whether the data and the nodes of the smart ambulance can be deemed as trustworthy in terms of integrity, resilience, availability, etc. So this is more or less the concept. And it's demo time. So what we will show in this case, hopefully you can see the terminals. So what I would like to show is a simple scenario of this use case. So we will run our Go application, and this is basically our trust assessment framework on the left-hand side. So we can see that the trust assessment framework has been initialized. It is listening to specific Kafka topics. All the different crypto keys for communicating with different components of the ENTRUST framework have been set correctly, though we are not going to see them in this demo. And we can see that we have defined different trust models for different use cases that we have envisioned. But in this context, we will focus on this use case of ENTRUST, where we can collect different traces, both as it pertains to the ambulance topology, so all this, the high-end device and the low-end devices. So that will allow us to provide evidence about the configuration integrity of these devices, but then we collect additional traces when it comes to the data being exchanged. So here we have basically our trust assessment framework waiting for new evidence from the operational phase, and now we will emulate 3 pieces of evidence being sent to our trust assessment framework. So the first 2 of them in this scenario are positive evidence, so everything are being reported properly without any misconfiguration or any misbehavior. But then the last one, the last piece of evidence will report something abnormal. So here we can see that our demo Kafka client reports 3 messages. So first of all, the first message is basically initializing the trust assessment framework, so we can ignore it. But then we have, in this phase, we have the first evidence being sent, then the second one, and finally the third evidence. And let's see how our trust assessment framework reacts. So first of all, it receives this, as I mentioned, the first message at time 0, where it basically says to the trust assessment that we want to initialize our trust model for use case 3.1. And basically a set of handshakes and a set of sessions are being established in order for the trust assessment framework to listen for new evidence. And then we can see here that, for instance, we collect our first bunch of evidence from our operational phase. And eventually, this will allow us, and let me go first of all directly into the result. This will allow us to derive an actual trust level of projected probability of 0.87 and some other numbers further down the line. But this is our actual trust level, and it is compared to our required trust level. So basically what we say in this logic is that as long as the evidence allow me to derive an ATL that is greater than 0.87, then the question of trustworthiness of the ambulance topology is basically true. So we can consider the topology as trustworthy. And the reason that this happens is because we can see some parts of our trust model here. So we can see the different trust opinions, that we have some belief factors with a specific uncertainty, both as it pertains to the vehicle itself, but also the data. But when these are fused together and provide the final outcome and final actual trust level, then the result is high. And what I would like to highlight here is that this is highly dependent on the requirements and the methodology depending on the domain's requirements. So, for instance, here we have selected that a set of evidence can be converted to X amount of belief. But as I mentioned at the beginning, for a different domain or for a different set of requirements, this might be completely different. So for this specific case, the set of evidence that I mentioned before allow us to derive a trustworthy state for our device. But if we scroll a bit below to the third sequence of evidence, and I think this is the case here, we have set in our third evidence that the size of bytes exceeds the expected size. So for instance, it is expected that for a sensor data, the pieces of the amount of bytes shouldn't exceed, for instance, 500 bytes. But if we see more bytes being appended to the payload, then this might raise a flag in this specific example. And we can see how this flag has caused a drop in the belief state of this relationship and increased this factor, which was previously 0. And this corresponds to the disbelief when it comes to the trust opinion at hand. And again, based on the aggregation method that I mentioned previously, so this of course can be domain specific and you can configure it depending on the requirements. But the idea is that the fusion of these new trust opinions coming from the third evidence, this creates an actual trust level which is below the 0.87 threshold. And consequently, based on the latest evidence, the trust decision when it comes to this smart ambulance is set to false. And of course, when such an information is being reported to our end application, this might trigger different controls to be executed. One of them could be completely isolate this device from the topology, or another one could be perform a software update to resolve or to patch a specific vulnerability that causes this drop in our actual trust level. And I think this more or less summarizes the demonstration. A final part, for instance, here is that, and this again comes back to the dynamicity of the trust assessment framework, is that in this very example, we consider that if no evidence appear in the trust assessment framework for a specific amount of time, which can be configurable, of course, then we consider this node as inactive, and hence it is get detached from the trust model in order to save up some resources and in order to alleviate some of the memory requirements of the trust assessment framework. Hence, we can see here that we are not anymore running any trust assessment queries because all our lists here are empty. And this is because, yes, we have stopped sending evidence for this specific ambulance emulated device. Hence, the trust assessment framework is currently empty. Okay, so I think this summarizes the demo. And okay, with this, I would like to conclude the presentation. I think we have some time left for some questions, if any.
Yes, we do, Nikos. Thank you for the demonstration.
Yeah.
For the last session and the recap, I would like to ask if there are any questions from the participants. Please raise your hands. Feel comfortable. I would like to notify that the videos, the recordings are going to be uploaded in the YouTube and also shared along with, let's say, some of the material that was presented from the speakers. No questions? No questions? Actually, Nikos, we had the final presentation for today. It was a very good recap. No questions were posed today. Everything seems to be clear, and of course the audience that participated has experience, let's say, on the field. Thank you very much, Nikos. Let me, before we close, give a recap. We are going to have our last webinar to be hosted on the 19th of May, same hour, but only 1.5 hours, about the formal verification. Just to keep notes, and you're going to receive updates with the link for the connection and the details. The last webinar is also organized by the REWIRE project and the ENTRUST. Will be performed by Collins and the University of Eindhoven, Technical University of Eindhoven, and the subject will be on the formal verification. So I think we can close after, let's say, more than 3 hours with demonstrations and presentations. I would like to thank all the speakers for their performances and all the participants for joining today's webinar. So we renew our let's say, meeting for next week, next Monday, with the last webinar organized by ENTRUST and REWIRE. And I would like to thank once more all the speakers for being here today and performing their presentations and demos, all the participants for joining, and of course the dissemination teams of the two projects and the coordination team of ENTRUST as well for the collaboration and let's say making tangible such a result. I would like to thank you all and see you next week. Thank you very much.